Okay, so now that we've been talking about gravity and energy, we can now go back to revisit and continue our discussion about orbits. So remember that when we talked about gravity way back in, I think it was chapter 6, when we were talking about Newtonian Dynamics of that, we said is that since central forces, the force points in the direction of the radial vector, so either in the same direction or in the opposite direction, i.e. collinear, what that means then is that the torque is equal to 0, which means that the angular momentum must be conserved, which tells us then that all the motion is within some sort of plane, and we can move within that plane, which means we're moving in an effective two-dimensional system. So since we're working in a two-dimensional system, that means then that we can work in plane polar coordinates. Since we have a 2D system. Now, just to remind ourselves, what we found was that if I had an object which is moving in, say, an elliptical fashion, where this was my angle of theta, what we found then was that the radius of this guy in respect to the angle is equal to alpha divided by 1 plus the eccentricity, which again tells me if it's a circular orbit or a elliptical orbit or hyperbolic orbit or etc. Which is also equal to A, which is the semi-major axis, so that's the longer of the two axes, times 1 minus the eccentricity squared, divided by 1 plus the eccentricity times cosine of the angle. So since we were talking about energy, what we can do is we can actually redo all of this in terms of energy, which will allow us then to determine how the eccentricity depends on the energy. So different energies then will give us different eccentricities, which will allow us to then put restrictions on the energy, as well as talk about the minimum energy and the radius at which this orbit, if I had a circular orbit, is allowed to be as. It'll allow us to get a better picture of what's actually happening as well in terms of energies and potentials. So good. So first things first is since we're working in plane polar coordinates, we know in this case our kinetic energy, which is equal to 1/2 the mass times the velocity squared, is equal to 1/2 times the mass times the velocity divided by the velocity. And way back in, I think it was chapter 2, we looked at the velocity in terms of plane polar coordinates. So if I dot that with itself, this becomes equal to 1/2 the mass times r dot squared plus r squared times theta dot squared. And remember that dot corresponds to the time rate of change of that quantity. So this is how the radial distance is changing as respect to time, and this is how the angle is changing over time. So for this tells us then that the total energy, I'm just going to call it E, is equal to the kinetic energy plus the potential energy, where the potential energy in this case is simply a function of the radial distance. Again, not directions because it is a central potential. So here I'm just going to write that this is a central potential as some variable v, but in a little bit we're going to specialize to gravity and call this guy u of g. So putting this together, this becomes 1/2 m times r dot squared plus r squared times theta dot squared, plus then whatever our central potential happens to be. Now, if I use now the definition of the angular momentum, and I solve this guy for him, so basically all I'm going to do is I'm going to do what we did back in chapter 6. Let's introduce a new parameter. Let's call it u, where u is equal to 1 over r, which means I'm going to turn all of my r dots then into a du d theta. So instead of looking at how this thing is changing with respect to time, we want to know how is changing with respect to the angle. Again, we want to find something that matches this guy over here. So, if we do that, what we find in this case then is that the energy is equal to the angular momentum squared divided by twice the mass times the rate of change of u with respect to theta, that quantity squared, plus u squared, all plus our central potential, again, is equal to the energy. So this is what's called the energy equation. So good. So basically, what we want to do now is use this guy and then specialize on the fact that our central potential is actually that of gravity. So I'm just going to replace the here with ug. So let's do that. And then from here, we want to determine exactly what these orbits are. And then from these orbits, we want to be able to replace the eccentricity with the energy, or at least know how the eccentricity depends on the energy. So here we're going to replace V is equal to U of G, which is equal to minus K divided by R, which is equal to minus K times U. So basically, the plan then is we're going to replace that V here with U of G, and then simply solve this for du d theta, and then use separation of variables to solve this first order differential equation. So let's go ahead and do that. So this is going to be the energy then is equal to L squared over 2m times du d theta, quantity squared, plus u squared minus k times u. So in this case, we're going to add this term to both sides, multiply by the inverse of this, and then subtract this guy, and then take a square root. So this gives me that du d theta, quantity squared, then is equal to 2m over L squared times e plus k times u minus u squared, or finally take a square root. I get then that du d theta is equal to the square root of 2m over L squared e plus ku all minus u squared. Now, since the right-hand side doesn't have any dependence on theta, we can simply multiply theta on both sides, make this side theta, divide this term over here, and then do an integral. So if we do that, we get the integral of the square root of 2m over L squared times then e plus ku minus u squared du is then equal to the integral of d theta from the initial angle theta initial to the final angle, which is the same thing as the final minus the initial angle. So this is all we have to do. So from here, all we need to do then is integrate the left-hand side. Now it turns out this left-hand side is actually pretty easy. Somebody has actually done it before. All we need to do then is look it up in a table. So let's go ahead and look that guy up in a table. So looking at a table, what we find is if we have an integral of the form of, so if I have a times u squared plus b times u plus c square root du, this is the same thing as 1 over the square root of negative a times the inverse or the arc cosine of minus b plus 2u divided by the square root of b squared minus 4ac. Now, if I use this and match to my terms over here, we can see then is that a is equal to negative 1. B then is going to come from this term here, so I'm going to get a 2mk over L squared. So B then is equal to 2mk over L squared. And then C is going to come from this energy term. So C then is simply equal to 2me over L squared. So if I take these, plug it into here, and then solve for u by taking a cosine of both sides, we can then solve for u, and then finally to get r, we just take the inverse of that. So I'm going to skip a bunch of algebra steps here, and then simply write out what the result is. So from here, what we find is that r is equal to L squared over mk times 1 plus square root of 1 plus 2el squared over mk squared, all times cosine of theta minus theta initial, 1 over that. Now, if I compare that guy to what I wrote down over here, we can then see that alpha then is equal to simply L squared over mk. So alpha is equal to L squared over mk. And then the eccentricity, which is this term, is then simply equal to that square root. So eccentricity then is going to be the square root of 1 plus 2e over k times L squared over mk. But L squared over mk from here is actually the same thing as alpha, so this is the same thing then as the square root of 1 plus 2e over k, all times alpha. So basically, this now tells me how the eccentricity depends on the energy. Now, before we talk about that, we can learn something else from here. And we can learn from here is actually using this guy, that alpha is related to the semi-major axis from him. So basically, what I can do is I can square both sides and then make alpha, or at least make it look like this particular term here. So before we move on and talk about how this depends on eccentricities or the energy, let's talk about that guy. So first off, let's square both sides of this. So I'm going to get an eccentricity squared that is equal to 1 plus twice the energy divided by k times alpha. Now I want to get that 1 minus epsilon squared, so I'm going to subtract that guy, subtract that guy. So I'm going to get a minus 2e over k times alpha is equal to 1 minus epsilon squared. Divide both sides by alpha, so minus 2 times e divided by k is equal to 1 minus epsilon squared divided by alpha. But relating here, 1 minus epsilon squared divided by alpha is the same thing as 1 over k. So I get 1 minus 2 e over k is equal to 1 over a. Or finally, this tells me that the energy is equal to what? Minus k divided by twice of the semi-major axis. So basically, this says that if I have an elliptical orbit, or at least some sort of closed orbit, like this, what has to be true then is that the energy is related to the semi-major axis this way, and that the energy has to be negative. So the energy that this particle, or this object has, is minus k divided by twice of the semi-major axis. And we'll talk about why that is necessary in just a minute. But note that this is another side effect from here. Well, let's go back to here. So let's go back to our eccentricity. So first things first is for eccentricity, what we said was to have closed orbits. We either have to have an elliptical orbit, or we have to have a circular orbit. To have an open orbit, or at least an unbounded orbit, so to have unbounded, meaning that this thing is either going to be a hyperbola or a parabolic. Now, to have an elliptical orbit, what we said was that the eccentricity must be less than 1. So now if I'm looking at my eccentricity here, to make this thing less than 1, what has to be true is that this entire term must be negative to make this thing less than 1. So for this to be true, what this implies to us then is that the energy must be negative. Now, for circular orbits, we know that the eccentricity must be equal to 1. For this thing to be equal to 1, the only way that's going to happen is that the energy is equal to 0. So here, we have to have it, the energy is equal to 0. For parabolic, we know that eccentricity is greater than 1. And for this to be greater than 1, we have to have then that the energy is positive, meaning that the total energy of the system is positive. Now, what does this mean? Now remember that, in our case, the total energy is equal to the kinetic energy plus the potential energy. But in our case, the potential energy is specifically the gravitational potential energy. But the gravitational potential energy is negative. So what that means then is what? To have a negative energy, that means this whole thing has to be negative, which tells me then that the kinetic energy must be less than the magnitude of the gravitational potential energy. So for this to be true, the kinetic energy must be less than the magnitude of the gravitational potential energy. For a circular orbit, for this thing to be 0, it just means this term and this term must be identically the same, which means the kinetic energy must be equal to the magnitude of the gravitational potential energy. For this to be true, it just means that the kinetic energy must be greater than the magnitude of the gravitational potential energy. Now, the question is, does any of this actually make sense? So, to understand if this makes sense, let's go back to our energy expression. So let's go back to our energy expression. So according to our energy expression, what we had was that the energy, or the energy equation, was equal to the mass divided by 2 times r dot squared plus L squared divided by r squared. Should be plus whatever the central potential is. Now again, I'm just going to go back to central potential in this case, and again, we'll specify the gravity in just a minute. Now again, here I'm just replacing that this was in terms of the angular momentum. Now let's split this up. So this becomes m times r dot squared all over 2 plus m times l squared over r squared plus the central potential. And this thing we're going to define then as the kinetic energy, which is m times r dot squared over 2 plus what we're going to call the effective potential. So this effective potential is split up into 2 terms. There is the potential, which comes from our central force, and there's also this term, which is what's known as the centrifugal potential. So to get a better understanding what this is doing, let's actually plot this effective potential. Let's plot it as a function of position. So on this axis, I'm going to plot the effective potential. On this axis, I'm going to plot R. Now, here, let's now again specialize to the fact that our central potential is actually the gravitational potential. So we know our gravitational potential goes to 0 at infinity, and then it's going to plot. So one more time. There you go. Go to 0 like this. Right? So this is u sub g. This guy, our centrifugal, this guy goes as 1 over r squared, but it's positive at all times because this is positive, positive, and positive, which means this guy is actually going to do something like this. Now let's look at some bounds. Right? As r goes to infinity, this thing is going to go to 0 faster than this one is going to go to 0, which means for large distances, the gravitational potential is going to be dominant. However, for short distances, since this goes as 1 over r, this goes as 1 over r squared, this one is going to be dominant for short distances, which means that my total potential, my total effective potential, is going to follow the centrifugal for the short distances, come down, and then it's going to start to follow that of the gravitational potential for large distances. So my total effective potential has this potential well in it. Now, what this means then is that for different fixed energies, I now have different results. So for example, when I have an energy which is less than 0, say this energy here, what we can see in this case then is we're going to have 2 different turning points. So we're going to have this turning point, let's call it r minus, and this turning point, let's call it r plus. So what's going to happen is that the object is going to get bounded between 2 radii, which means that what? Again, if we go back to our picture, here's m, here's the object. That means this distance here is going to be r minus, and this distance here is going to be r plus. So this thing is bounded between these 2, where it's oscillating back and forth between those 2 different radii. For a positive energy, say here, what's happening in this case then is that what? The object is coming in from infinity, going to interact only with then the what? Centripetal portion of it, slingshot around the object, and then get sent back out to infinity. So meaning that what? If here is my central body of m, this thing's going to come in, basically slingshot, and then get sent back out, where this is only going to have 1, which is then r minus. So this is going to have 1 turning point due to the fact that this thing gets wrapped around and slingshotted. Now, for 0 energy, basically what's going to happen then is that this radius and this radius are going to combine together to be 1 radius, meaning there's only 1 turning point, and that 1 turning point will then be the circular radius at which this thing orbits about. So the pure fact that this thing had to have a negative energy, again, must be true due to the fact that this thing is bounded. So the next thing we want to know is, where are these turning points? So where is r plus and where is r minus? And just like we did earlier, to determine the locations of the turning point, what must be true then is that the kinetic energy must be equal to 0. So that means that our energy, which is equal to the kinetic energy plus the effective potential, this term simply has to be equal to 0, which means the total energy must simply be equal to the effective potential, which means that 0 must be equal to the effective potential minus the total energy of the system. Now, plugging in our effective potential, so again, this is going to be equal to ml squared over 2r squared, plus my gravitational potential, which is minus k over r, minus the energy must all be equal to 0. Now, if I take this guy, multiply it through by an r squared, that's then going to allow me to determine these locations. So let's do that. So plug this in. So basically what we're going to get is a minus er squared minus k times r plus ml squared over 2, then must be equal to 0, which gives us a quadratic equation to be able to solve. So in this case, we get r then is equal to minus b, which is simply k, plus or minus the square root of k squared minus 4 times a, which is negative 1. So that becomes a positive times e. Right. All times him, which is then m all squared over 2, all divided by negative twice of the energy, divided by 2 times a. So this guy cancels that, becomes a 2, so it's going to be k plus or minus the square root k squared plus 2 times the energy times m times l squared, all divided by negative twice the energy. Okay. Let's call this r plus or minus. So good. So again, going back to the fact that what? To have a closed orbit, so again, if this guy is going to be a elliptical orbit, the energy must be negative. If the energy is negative, that makes this term negative, which means that the discriminant here is less than this first value, which means that what? Both of these are going to be valid. And this negative is going to cancel out that negative, which makes it positive. So basically, the fact that the energy is negative gives me 2 positive roots for my quadratic, which means I have those 2 turning points, which again correspond to these 2 different radii. Now, to have a circular orbit, what has to be true in that case then is I have to have a minimum amount of energy, which is determined by the fact that the discriminant here has to be equal to 0, because in that case then I'll have one particular orbit. So in this case, if I set my discriminants equal to 0, we find in this case then is that the minimum amount of energy that this thing needs is then going to be equal to minus k squared over twice the mass times L squared. Plug that back into here. This then tells me that what? The radius of this circular orbit is then equal to minus k divided by twice the minimum amount of energy. Now, when we had a positive energy, what happened in that case then is this thing is still positive, which means that this thing is bigger than him, meaning the discriminant is actually bigger than this first term. This is positive, which means this is negative, which means we can only keep this negative root, since positive root would give us what? A positive answer here, but then a negative answer here. Or again, here the negative root is going to give me a bigger value of negative, overall negative divided by a negative, which makes it positive. Anyways, the point is that whenever I have a positive energy, there is only one positive root, which means that there's only one possible radius in that case. So again, corresponding exactly to that picture. So again, the fact that the energy is negative is essential due to the fact that, again, there's this potential well was present from this effective potential, meaning that for this thing to have a closed orbit, again, I have to have a negative energy to ensure that I'm inside of that potential well. If I don't have a negative energy, I'm outside of the potential well, and then this object is just going to undergo scattering, which will be the topic that we're going to talk about next time. Now, the next thing is, just because I have a circular orbit doesn't mean that circular orbit is stable. So for example, if here's my central body, here is my circular orbit, so this guy has R0. Just because this thing can move under circular orbit doesn't mean that it's going to be a stable orbit. So for example, when I'm talking about, say, a black hole, and I have a photon which is orbiting around the black hole, it turns out that that is not a stable orbit. So if I had this thing on on a circular orbit, if I perturb it in one direction or another, meaning if I blow on it or kick it or do something like that, it's going to fall directly then into the black hole. So what I want to know in this case then is what possible central forces can I have, meaning what types of possible structures of central forces can I have which will allow for me to have a stable orbit. So again, all this means is if this guy is sitting here, and then I perturb it in one direction or another, so let's say I move this by some delta r here, is this thing just going to wobble, but end up still being under some sort of stable orbit, or is this thing going to do something different, which is actually, say, in spiral, and then crash into the central body? So this is what we want to know. So first things first, we want to know then is what happens at the circular orbit. So first of all, when we're at a circular orbit, when r is equal to r0, this means then that what? R dot is equal to r double dot, which is equal to 0. So we go back to the Newtonian formulation, which was m r dot is equal to ml squared over r cubed plus the central force. At my circular orbit, this term is simply equal to 0. So here I'm going to get 0 then is equal to ml squared over r0 cubed plus f of r0, which means that at the circular orbit, my force is equal to negative ml squared over that radial distance cubed. So now, since we're here, we now want to perturb our system. So again, we're going to grab it, pull it, or push it by very small amounts, which basically means that now what I want to do is say that this distance from here to here is going to be a distance of x, which is then going to be the same as that perturbation distance minus then the original orbit or the circular orbit. So what we're going to do then is basically use this into this expression and then use and figure out what the dynamics are about this new radius of x. Where again, this small amount here is our delta r. So if I plug this in, what I get in this case then is that mx double dot is then equal to, so it's going to be an ml squared over x plus r0 cubed plus f of x plus r0. Now, presumably, we're going to say is that what? This x is some sort of small quantity. Again, we're looking at how this thing is actually changing. So ultimately what I want to know then is what? I want to Taylor series expand this guy. So first let's pull out him. So this is going to be equal to ml squared over r0 cubed times 1 over 1 plus x divided by r0 cubed plus, and again, if this is small, this is going to be f of r0 plus x times f prime of r0, where this is actually to be read as the first derivative of the central force with respect to x evaluated at x is equal to r0. Now again, since this is small, I can Taylor series expand this guy, so this is going to be approximately equal to ml squared over r0 times 1 minus 3 times x over r0 plus higher order terms, no matter what about those, plus f of r0 plus f prime of r0. Now note this term here, based off what we have over here, is actually negative fr0. So this term here is actually negative fr0, which means that this first term here is going to cancel with this term. So this becomes then equal to 3x over r0 times f of r0 plus f prime of r0. So let's factor out, I'm sorry, I dropped my x here. There we go, that x. Let's factor out the x. So let's write this then as negative x times negative 3 over r0 times then f of r0 minus f prime of r0. So you may be wondering why I actually pulled this thing out to be a negative. Well, what we want to do is say that this thing is simply oscillating and this thing is oscillating as a spring mass system. That's basically what we're going to say. So again, sorry, this distance here is delta r. This little distance here is x, right? So we're basically saying that this thing is acting as a spring, which is moving by an amount of x away from that equilibrium position, which is that r0. So basically means that I want to write this then as Hooke's law. So ultimately, what this means then is, let me plug this into here, is that what we're saying is that we have an mx dot is equal to minus k times x, where if I identify here with here, what this means then is that k is equal to negative 3r0 f of r0 minus f prime of r0. This is my k value. Now, for this thing to be stable, what means is that we have to keep this thing to be positive. So if we want this to be a stable equilibrium, what this means then is that k must be positive, which is equal to negative 3 over r0, f of r0 minus f prime of r0 must be positive. Or if I multiply through by the negative, I get a 3 over r0, f of r0 plus f prime of r0 must be less than 0. Right? This thing has to become negative to make sure that this thing is some sort of stable equilibrium. Now again, our goal is to use this to determine what is the structure of F. Okay, so this is what we want to know. So what is the structure of F? Now what that means is we're going to assume that our central force goes as some sort of constant r raised to the nth power. So basically all I want to know is what is the n dependence, or what is that distance dependence of this central force. So we want to figure out what is that n. So let's take that and plug that in. So this is going to be equal to 3 over r0 times c times r0 raised to the nth power plus n times c times r0 n minus 1, and this has to be less than 0. Good. So this r0 here is going to cancel one of those, so that's going to become a negative 1. This c is the same as this one, so we can get rid of that. This r is the same as this one, so this gives me 3 plus n must be negative, which means then that's what? Bring this over here, so this means then that's what? N must be greater than negative 3. So what this means then is that what? To have stable orbits, what has to be true is that we have to have a central force, f of r, which is greater than this central force, which is c r to the minus 3. Which means something like Newtonian physics, or Newton's universal law of gravity, which has a central force which goes as c times r raised to the negative 2, is greater than this guy, which then allows us to have stable circular orbits, which is good for us because, again, we have the moon. The moon is in approximately circular orbit around the Earth, but there are other forces pulling on it all the time, so things like the sun, Saturn, Jupiter, etc., that are giving it small forces, so small pulls in different directions as it orbits through the Earth. But what happens is that the moon is actually wobbling around the Earth, such as this, and it's not either being pulled away towards those or being pushed in towards us to inspiral with us. So these are, in fact, stable orbits. So again, as long as n then is greater than minus 3, then we have to have some sort of stable orbits.